Okay, so does everyone kind of understand a little bit about this equation here? And now it's time to confront reality. Okay? This is a set of simultaneous equations. For each s, we have u of s defined in terms of, you can think of this as a giant summation where we have u of all the states you could transition to. And luckily, we've got one of these equations for every possible state. So we've got, if there are n states in the MDP, we've got n equations in n unknowns. And in high school, you all learned that you can solve simultaneous linear equations, right?
Yeah.
So what's the problem?
Two variables takes, and that's three variables.
No. It's got a deeper problem than that. This is not...
Variables point at each other.
No, that's no big deal. You did that in high school. Simultaneous linear equations. There's only one problem. This is not a linear equation. It's got a max in it. Max is not a linear function of its arguments. If it were, then we'd be golden and everything would be fine, and we could solve this we'd take some big matrix math thing and say, solve. It would be n cubed time, and if you had n states, but we could at least solve it. Unfortunately, these are simultaneous nonlinear equations. So, gulp. What do we do?
What does that make for time?
Sorry?
You said if it was linear, it'd be n cubed.
Yeah, we'll deal with that later.
Okay.
I just want to get it possible now. Then we'll worry about making it fast. Premature optimization is the root of all evil. It's not mine, that's Knuth's, I think. Okay, so Bellman looks at this, and he's a professor at Princeton, so he's like, oh, whatever, I'm super powerful. Nonlinear, it's a huge set of simultaneous nonlinear equations, doesn't scare me. You know what I'm going to do? Huh. I'm just going to write down random values for my u's. Because I'm Bellman. So Bellman writes this down where you initialize u to whatever you frickin' feel like, for example, 0. And then you take your u's and you use them to derive a new set of u's. Let's call them u prime. And you say u prime, okay, u is supposed to be, I get some current reward, and then I look at, for every action, I look at the expected future reward. This is only an estimate right now. In fact, it's a pretty poor one, like 0. But hey, it's something. Right now it's all 0, actually, so this whole thing doesn't matter. So the first thing we do is we set u prime equal to the immediate reward we get. We do that for every state. Okay? And then we say, all right, I like that, I'll keep it. We go around this loop again. Now, when we enter here, we say, okay, this new u prime, all right, it's the immediate reward plus it's the expected reward I'll get at the next state. And I maximize over actions. It's a little bit more accurate because I'm taking into account not just the immediate reward in S, but also the reward I'll get in the very next state that I transition to. So we set that in. Now the action we choose here might not be the truly optimal one for the real MDP, but the u function is better than it was before. It used to be 0. Now at least it's got the r in it. And so now I have my new u primes. And these new u primes are doing like a one-step look ahead, you can think of it as. Right? I got the immediate reward plus the reward of the future state. Now I set that to u and I go around again. And now I've got the immediate reward plus the expected future value of the state I transitioned to, and this u is already corresponds to a one-step look ahead. So now when I do this evaluation here and I compute this new u prime, these new u primes have done 2 steps of look ahead. And I go around and around and around and around. These equations are being computed using larger and larger look-aheads. And in fact, Bellman proved, the reason that he is in the pantheon of AI, is he proved that this converges. And in fact, he also proved there's only one thing that it can ever converge to, which is the true, honest-to-God, future expected utilities. So you start with 0 for everything. You run these updates an infinite number of times, granted, but you run them for a while. They will converge to the optimal values. That's very impressive. That's happiness. If you're an AI person, that's one definition of happiness, is to converge to your optimal values. And let's see, the algorithm is called value iteration. This is called the value function. These are called Bellman updates. For infinite updates guaranteed to reach equilibrium, equilibrium is a unique solution to the Bellman equations. The Bellman equations are just those simultaneous nonlinear equations. Sir?
So you can stop short and get an approximation.
Pooh! Always one step ahead. Always one step ahead. Yeah. Exactly right. So what stopping is the next slide. Yeah. We'll talk about that in a second. Yeah. You can, if you stop early, you're not guaranteed to have the optimal value function. However, it's going to be pretty good. And in fact, on the next slide, I have some equation-y thing that bounds the badness. Yeah. But I don't want to go there quite yet because we just had this enormous, for me at least, leap and moment. So I just want to just enjoy that for a second. In fact, I don't want to just enjoy it. I want to show it to you using Java technology. Here's a world, a grid world, and love and happiness is here. Badness is here. There's like a evil pit here, and here's the pot of gold. I think is there a pot of gold up there? Maybe. I think maybe there is. It's something like that. Yeah, maybe there's minor reward here and huge reward down there. I forget the.
It's better than all of its neighbors.
Yeah, it just looks like a sort of.
I think there's huge reward here. I think I think there's a little bit of reward there.
It just looks like. It looks
Maybe there's some probability of going off the side of the world. I think this is with an uncertain movement model. So I think when you go forward, there's a probability like 0.8 that you move forward, and a small probability you go to one side or the other. So there might be some advantage in staying away from the wall. I forget the exact dynamics, which is a little embarrassing. Does it say here at the bottom? There are 4 actions. 0.7 chance of doing the right thing, and 0.1 chance of going on all the other directions. Ooh, if you bump into the wall, penalty of 1, meaning a reward of -1. There are 4 rewarding states. 1 worth 10, that's got to be that one. 1 worth 3, and that must be the one up here. 1 worth 3, 1 worth -5, and 1 worth -10. So this is a -5, I guess, and this is a -10.
The darker red.
Right there.
Yeah.
That one right there. Yeah. That's the -5. This is the -10. Cool. All right. So we start. These numbers represent the value function, and these arrows correspond to the policy that you would take if you believed the value function. So like I'm here and I'm wondering which way to go. I look at the value. It's equal everywhere, so I don't go anywhere. I don't have my policy is like, I don't know. So notice we have 0 everywhere. So I do one Bellman backup. Pching. And so now the value function reflects just the immediate reward at each state. Right, so we have -10, -5, that's +10, that's +3. Yeah. Yep. You want to stay away from the walls in this world. Ouch, that hurt. I do one more step, value iteration. Ba-ching. now you can see that being here is bad just because, not because you are going to go, you're going to take that action that has a high probability of going in there, but just no matter what action you do, there's actually a small probability of transition into there. So even if your policy is like, go anywhere but there, there's still a negative state because there's always that stochasticity that'll make you fall in there. Similarly, these guys, the action you want to do, the policy you'd select is to go there. So your action is this minus times the discount factor. The probability that you'd actually end up here, though, is only 0.7. So I guess it's 0.7 times times 9.8. Because I guess once you're here, you can't just stay there. You have some probability of transitioning out. So that's a little less than 10. So this is 0.7 times a little bit less than 10. So you can see the value functions start to take shape as we do more and more steps of value iteration, again and 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 again. You can see the numbers are starting to settle down, actually. They're not changing that much. And if I press it a lot, now they're stable. We've reached equilibrium. And that's actually the optimal policy. So if you're next to the wall, you want to go away from it. If you're here, you don't want to go away because you might hit this. I don't know why you don't go away here. That's interesting to me. It's the optimal policy.
Why you don't go away?
Why you don't scoot away from the wall?
Yeah, why wouldn't you scoot away from the wall?
You have a higher. If you probably
Is it,
lower the
You
lower
only-
the discount, you probably go away from the wall. But it's probably like, oh, there's a 10. Like,
Well, you're going to have to go over when you get down here anyway. So why not go over here?
I would say because you probably have a better chance of getting there safely than using one whole cost to get away from
That's true. Because if you're here, well,
it. Or it thinks
no.
that's what it thinks. Maybe.
No, this is the optimal policy. I mean,
yeah,
this is the great thing about math is it's actually true. So this is the optimal thing to do. Maybe if I read the problem description a little more carefully.
the odds of you going off the grid are so small, but
Here you go around, here you go down here rather than go here and then go down. Because if you're here and try to go down, there's some probability you'll fall into the -3. So you already are trying to go down here. So that makes perfect sense. Here you're going down and around. That makes sense.
The numbers are lower on the edge, but not the
Yeah, so this is the expected reward. If you behave optimally from here, it's like not as good a world to be born into as if you're over here.
do the arrows point at the highest value that they're touching?
The arrows show the policy. So we haven't talked much about the policy. So yeah, let me go back to the slides. If I compute the value function, I mean, this is why it's so exciting to be able to compute the value function. If I know the true value, future expected reward that I'll get by being in every state, then the optimal policy is just to take whatever action gives me the greatest expected value. Like this is like a one-step look ahead policy where if I know the true heuristic value at every possible successor, then I can be greedy with respect to that heuristic. And I will have done the optimal thing. In a sense, these Bellman backups are constructing the perfect heuristic function backward from the goal. And now to act, I can just be greedy with respect to that awesome heuristic. So this is the simplest, most popular way of solving an MDP. You compute the optimal value function and then act greedily according to it. Done deal. Any questions about that? Everyone understand value addition? Nathan?
Can you derive the third equation from the second one?
No. They are the same equation. I mean, this R is the first R in the expansion, right? And then this is, here's this summing, this taking the weighted average over all the states you could go to by taking the best action is doing the expectation for you. So it's really the same thing.
But you said no, you derive it.
I changed my mind. Frank.
So we know that it converges uniquely for a given place. And is there any way to utilize that so we don't have to run through all of the repeated steps over and over?
You're talking about efficiency. What did I just say about the root of all evil? Jonathan, can you remind us?
Premature optimization is the root of all evil.
Frank, take that to heart. It's a lesson for a lifetime.
It's a few slides ago.
Right here, we're going to, this thing here called sweeping, that I've got like a couple more classes on MDPs, and we're going to talk about wonderful, cool algorithms for solving them that are way more efficient than this stupid, ancient, bull-headed, baby algorithm. So don't worry. But first steps first, okay? I'm still basking in the glow that these equations are even solvable, and you're already bitching about efficiency. Jesus.
So, is there something that makes the discount non-arbitrary?
Wow, that cuts deep. Okay. The discount. So Dan's like, this discount, is it just a mathematical trick to make the thing not go off to infinity, or does it actually have some meaning? Like, if my boss walks up to me and says, solve this inventory problem, what the hell do I set the discount factor to? I don't know. It's a good question. Usually when there's money involved, you can say that thing I was saying to Jonathan earlier about like net present value kind of stuff. No, not that. Really? Uh-oh. It will cost you, yeah. Premature optimization will cost you money. So you could do that kind of an argument if it involves money. If it's like some robot walking around, then what do you set it to? I'm going to faintest idea. To whatever value gives you decent behavior. We're working towards what you're going to need for assignment 4. Assignment 4 is about reinforcement learning. Anyone know what reinforcement learning is? Okay, what's reinforcement learning, Adam?
Running through data set or something and get the outputs. And then
I'm sorry, running through what?
some sort of data set with the outputs from the function and trying to work out how to do things to get the correct output.
How to get the correct output. Yeah, where the function you're optimizing is the reward function. So reinforcement learning is the baby problem. You're born, you're at S0, you've got these actions, you do them, you get rewarded each step. Someone either changes your diaper or hits you on the head, or you hit yourself on the head. I don't know if you guys have ever seen like a newborn kid, but they're just totally helpless. It's amazing. Like, what?
Is it like operant learning?
Yeah, operant conditioning. Conditioning, yeah, reinforcement learning, exactly. So you get feedback. So certain things work, certain things don't work. Learn to optimize the reward function for every state. Figure out a policy. And so it's exactly solving an MDP where you don't even know what the transition function is. So that's what we're working towards. So that's why I'm not too worried about the discount factor, because like in the real world, you may not even know what the transition function is completely yet. You may have some idea, but like trying to optimize the 10,000th step from now, like the chance you'll be in the state you think you're going to be in is like super small. So like worrying about 10,000 steps from now, don't even think about it. So, my advice would be like 0.9 and go. But
whatever gives the best results.
well, obviously. Okay, so other questions about this? Frank?
So mice learn the best with the reward being unpredictable.
I have no comment on that.
That would-
Well, actually, I do have a comment on that. We'll talk about that later. That's my comment on that. When we get to reinforcement learning. We're not doing reinforcement. Right now, we have the MDP. Someone gives us T, they give us R. Right? There's people in this room who are probably feeling a little bad just being given T and R already, and they're like, yeah, this is yucky. So let's get comfortable with this, and then when we're all comfortable and we feel like being given T and R is like too easy, then we'll deal with the case where we don't even know what it is. So.